Today we're going to be talking about Thevenin and Norton equivalent circuits containing dependent sources. And then after we wrap up the lecture, as usual, there is an in-class assignment, but there's also a mini lab. Realistically, the mini lab does not take particularly long, only 15, 20 minutes tops. Once you have the circuit set up, it is literally just adjusting the dial on your multimeter. You don't have to move literally anything. There is going to be a little bit of an issue with measuring the Thevenin equivalent resistance of your network because the power supplies that we have in this room have a finite amount of internal source resistance. So when you're measuring your Thevenin equivalent resistance, it's probably best to actually take out the banana plugs that go into your power supply and literally physically short them, and then you'll get something much, much closer to what you would mathematically predict. All right, so Thevenin equivalent circuits with dependent sources. Or Thevenin and Norton equivalent circuits, really. So we are just going to learn this process by doing an example. And until we get to the resistance, it's going to be exactly the same thing that we did in class last Wednesday. Okay. So if I have the following circuit where I've got a 10-volt source connected to a 3-ohm resistor connected to a 2ix current controlled voltage source like so. I've got a 6-ohm resistor down here through which my current Ix will flow. And lastly, I have a 5-ohm resistor here. And my ultimate goal is to determine Thev and Norton equivalent circuits. And I'm going to say explicitly positive polarity will be on top and the current reference direction is down. So do you guys want to solve for Thevenin voltage or Norton current first? So I think I heard 2 people say voltage and 1 person say current, so we're going to go with voltage first. Okay. So we're going to do the exact same thing that we did on Wednesday. I'm just going to say that the Thevenin voltage is the voltage drop that appears across the open circuited terminals of interest. That should have been a 3. Here is my VTH that we're solving for, and I would like a suggestion from you all as to how we might go about solving this. So we definitely could do nodal analysis, okay? There are only 1, 2, 3, 4, 5 nodes in this system, if I'm counting correctly. So 1 at the top left, 1 between the 3-ohm resistor and the voltage source, 1 between the voltage source, the 5-ohm resistor, and the 6-ohm resistor, 1 on the right-hand side of the 5-ohm resistor, and one on the bottom, but we could make some observations that would effectively wind up eliminating at least one of those nodes, and one of them would be ground. So I think we'd wind up with a 3-equation, 3-unknown system here. So that's certainly one way to do it. It is not the way that I would do it. Anybody else care to venture a guess as to what I would do? Mesh. Also, you're more right, but you're still wrong. So let me explain what I mean by that very specifically. There's only one mesh here because there's only one closed current carrying path. So what I would do would be Kirchhoff's voltage law. So let me explain things really quickly here, okay? How much current is flowing through that 5-ohm resistor on the top right there? 0, because it's not part of a closed current carrying path, right? So if there's 0-volt drop across that 5-ohm resistor, then effectively we could just move the Thevenin voltage over to the left and treat it as if it were the voltage drop across that 6-ohm resistor, because of Kirchhoff's voltage law, right? So essentially what I'm analyzing here is just a single loop circuit because the 5-ohm resistor isn't going to do anything. So I could set up a system of equations, or I could fall back on the basic fundamentals, KCL, KVL, and Ohm's law, and get the result that I'm looking for much, much easier. So that's what I'm going to do. So applying KVL around this loop, I'm going to wind up having negative 10 volts plus 3 ohms IX minus 2 IX plus 6 ohms IX is equal to 0. Since IX is literally the only current that's flowing in my circuit, I'm just using that as my variable as I follow my current around. So rearranging this guy, I would have 10 volts is equal to, let's see, so 3 minus 2 is 1 plus 6 is 7 ohms times IX. So IX is 10/7 of an amp, and VTH, just using Ohm's law, is 6 ohms times IX. So 6 times 10 is 60/7 of a volt. Anybody have any issue with my algebra? I haven't finished a cup of coffee this morning yet, so it's very likely that there's a mistake here. I don't think there is, but my brain is not functioning on maximum caffeination yet. Well, I'm not assuming it's a resistance, but because it is a current controlled voltage source, that 2 has units of volts per amp, which is the same thing as an ohm. So dimensionally, it behaves like it was kind of like a resistor. So any questions, comments, concerns about how we solve for VTH here? All right. So now let's find I Norton. So to find the Norton current, I'm just going to redraw this circuit, but now I'm going to short circuit those 2 terminals. And my ultimate goal is to find the current flowing through that short. So here's my 10-volt source. Three ohm resistor. Two IX voltage source. 6 ohm resistor through which my current IX flows. 5 ohm resistor. Now I'm simply shorting those 2 terminals, and my Norton current will be the current flowing down through that short circuit. So how might I go about solving this one? I'd probably do mesh as well here. Mesh seems like it would probably be the quickest and easiest way. I was thinking about being a smart ass and seeing if I could do it with current division, but it'll be a little bit harder because that IX current winds up or the current flowing through the 3 ohm and the 2IX voltage source is no longer just IX, and so it'll make it a little bit more difficult to do. So I think mesh analysis is probably the easiest way to go. So I'm going to call this guy right here mesh current IA, and this guy right here mesh current IB. So what would my controlling variable relationship be? IX is going to be equal to what combination of mesh currents? IA minus IB. Okay. I don't have any current sources, so I won't have any current relationship equations, nor will I have any super meshes to deal with. So I think I'm just left to write a KVL equation around mesh A and a KVL equation around mesh B. So around mesh A, that's going to look like negative 10 volts plus 3 ohms IA minus 2IX plus 6 ohms IA minus IB is equal to 0. And then around mesh B, this is going to be 6 ohms times IB minus IA plus 5 ohms times IB is equal to 0. And now I'll solve this system for IA, IB, and IX. And let me scooch that over actually. We could see, I hope pretty easily, that our mesh current IB is going to be the exact same thing as our Norton current. So I'm just going to go ahead and write that IB is equal to I Norton. So putting this into my calculator as a 3x3 system, and my first equation, my coefficient for IA is 1. My coefficient for IB is -1. And my coefficient for IX will be -1 when I move it to the other side of the equal sign because I'm treating it as a variable. And then my constant term is going to be 0. In my second equation, my coefficient for IA is 3 plus 6. My coefficient for IB is -6. My coefficient for IX is -2. And my constant term is +10. In my third equation, my coefficient for IA is -6. My coefficient for IB is 6 plus 5. My coefficient for IX is 0. And my constant term is 0. So when I solved this system of equations, I got IA to be 110 over 53 amps. IB, which is I Norton, to be 60 over 53 amps. And lastly, IX to be 50 over 53 amps. Did anybody else get a similar result? Okay, several people shaking their heads, so I'll assume I got that correct. Okay, so putting these two pieces of information together, we should be able to say that our Thevenin resistance is simply the ratio of our Thevenin voltage divided by our Norton current. So that would be 60 over 7 volts divided by 60 over 53 amps. And if my mental faculties are working correctly today, that's going to look like 53 over 7 ohms, but I'll throw that in my calculator to just make sure. Yep, 53/7. Or for those of you that prefer decimals, 7.571 and some change. Now, it would be handy if there were a way to verify that this was correct. Okay. So let's call this guy down here finding RTH. Okay. So in all of our circuits that we dealt with on Wednesday, we didn't have any dependent sources. And so what we did to find our Thevenin equivalent resistance directly was we looked at a dead network, and then we looked in through the terminals of that dead network and simply performed resistor combination techniques, okay? So I'm going to draw the dead network here. So that means my 10-volt source is off. Here's my 3-ohm resistor. I can only turn independent sources off, which means my dependent sources have to stay on. So there's my 2ix source. Here's my 6-ohm resistor through which the current Ix is defined. And then here is a 5-ohm resistor, like so. So my question to you all, and this is supposed to be an easy question, I just wanted to make that clear, is can we apply resistor combination techniques to this network to find out what RTH is? I see a lot of you shaking your head. Yes. I am saddened by that result. This network has an element that isn't a resistor in it. So how do we deal with that? We literally can't use just resistor combination techniques here, right? So as it stands, my 5-ohm resistor isn't connected in series or parallel with my 6-ohm resistor. My 3-ohm resistor isn't connected in series or parallel with the 6 or the 5. There is literally no resistor combination that we can do to this circuit. So we have to come up with an alternative method. Well, way back on the 3rd day of class, we learned about Ohm's law. And we actually did an experiment at the end of the 2nd day of class where we measured the voltage drop across the terminals of a network, measured the current flowing into the network, and the ratio of those two quantities was the resistance of the network. So we are going to have to use that fundamental definition of Ohm's law. The resistance is the ratio of the voltage drop across the terminals divided by the current flowing through the terminals, and what's called the test source method in order to figure out what this Thevenin resistance is going to be. So essentially, if I have a network that contains a dependent source and I want to find the Thevenin resistance directly, I have to externally excite this system as a dead network and then measure the voltage drop across the terminals and the current flowing through the terminals and take the ratio of those two quantities to find the resistance. If I've done my previous steps right, the result of that test source method analysis will be the exact same answer here. Okay? So we can choose to apply either a voltage source or a current source. So I'm actually going to wind up doing both to prove that we should get the exact same answer every way we approach finding the Thevenin equivalent resistance for a network like this. So I'm going to start with a voltage source, okay? So let me just make some notations here. So my goal here is to determine the voltage drop across the terminals of my network, as well as the current flowing into the terminals of my network. And then I'm just going to take the ratio of V test to I test. So if I choose to apply a voltage source, I'm effectively saying that V test will have some specific value. And when I choose to apply a current source to excite my system, I'm essentially saying that I test will have some specific value, and I'm just solving for the other piece of information, okay? Now, it turns out that because these systems are linear, we can literally choose any voltage source we want. So it could be a 1 volt source, it could be a 100 volt source, it could be a 37 millivolt source, whatever we choose, we will get the exact same answer every time because of the linearity of the system. Similarly, when we choose our current sources, it doesn't matter if it's direction up or direction down, if it's 1 amp, 1 milliamp, 1 gigaamps. Again, none of that remotely matters because of the linearity of the system. We'll get the same result for the Thevenin resistance. So I want somebody to just choose a voltage value. 1 volt, okay? Positive polarity on top or positive polarity on bottom? Top or bottom? Top, okay. So here's our 1 volt test source. And now our goal is to just figure out what that current I test is going to be. So what circuit analysis technique do you guys think would be the most useful here? Probably mesh. So let's call this mesh current IA and this mesh current IB. We don't have any current sources. We do have our controlling variable, so let me do that real quick. So what is our controlling variable IX going to be in terms of our mesh currents? IA minus IB. Great. Now we're just going to write our KVL around mesh A and our KVL around mesh B. So this is going to look really similar to what we did to find our Norton current here. So we're going to have 3 ohms times IA minus 2IX plus 6 ohms times IA minus IB is equal to 0. Around mesh B, we're going to have 6 ohms times IB minus IA plus 5 ohms IB plus 1 volt is equal to 0. And I don't think I've made any mistakes here, but let me just double check. So 3IA minus 2IX, 6IA minus IB closes that loop, so equals 0. 6B minus A, 5B plus 1 volt, back where I started. Okay. So I'm going to solve this system for IA, IB, and IX. So it's a 3x3 system. So in my first equation, my coefficient for IA is 1. My coefficient for IB is -1. My coefficient for IX is -1. My constant term is 0. In my second equation, my coefficient for IA is 3 plus 6 is 9. My coefficient for IB is -6. My coefficient for IX is -2. My constant term is 0. In my third equation, my coefficient for IA is -6. My coefficient for IB is +11. My coefficient for IX is 0, and my constant term is -1. And so when I solve this system, I get IA to be -4 over 53 amps. IB is -7 over 53 amps. And IX is equal to +3 over 53 amps. So what is, sorry, not my Norton current, what is my test current going to be in this system? I disagree. I also disagree. Negative IB. So IB is flowing from left to right through that 5 ohm resistor. I test is flowing from right to left through that 5 ohm resistor. So IB is negative I test, or I test is negative IB. Is positive 7/53 amps. And then I'm going to use this result over here. So my Thevenin resistance is just V test over I test is 1 volt over 7/53 amps, which I hope obviously comes out to 53/7 of an ohm, the exact same answer we got earlier. So any questions about applying a test voltage source in order to find the Thevenin equivalent resistance? Yes, ma'am. So the 1 volt drop doesn't, the 5 ohm resistor does not just see a 1 volt drop across it because the 5 ohm resistor isn't in parallel to that 1 volt source. Yeah. So that's why we have to do the full analysis. If it was in parallel, we would probably still have to take into account everything to the left that might also be in parallel as well that's going to contribute to that test current. So we're still going to have to wind up analyzing the whole thing. Any other questions? All right, so let's repeat this, but now we're going to apply a test current source. So starting once again with my dead network. And once again, our goal here is to figure out the voltage drop across our network and the current flowing through our network. We're going to use a current source. Somebody pick a value. 1 amp seems reasonable. Direction up or down? Up. Okay. So picking 1 amp up essentially says that I test is 1 amps. And so now all we have to find is that voltage V test. So how might we go about finding that voltage V test? So we could do mesh, but if we do mesh, I would say like V test is going to wind up being, let's see, -5 IB plus 6 ohms IA minus IB. Like that's maybe, it's not a ton of extra work because there's only 2 meshes, and then we'll have to effectively write another KVL relationship to find out what V test is. But let me look at this real quickly. I'm sorry, what? Oh, no, you're, so it'll be -1 amp. So fair enough. Yeah, okay, let's give mesh a whirl. Probably nodal analysis, just because I'm looking for a voltage. But with nodal analysis, I'm going to have, let's see, so I have my whole bottom node. I've got the node between the 3 ohm resistor and the voltage source. So that's one. The node between the voltage source and the 5 and 6 ohm resistors, so that's 2. And the node between the 5 ohm resistor and the 1 amp source, so that's 3. So it's a 3x3 system where all three quantities are actually unknown, and I got to solve for V-test directly. Or I have a 2x2 system where one of those two things is already known, and then I have to write a KVL relationship at the end to solve for V-test. So I think those are roughly equivalent difficulty. Yeah, so that's the one I count. So I'm counting the bottom as ground, and I don't have to write equations with ground. So that's why I'm saying it's a 3 equation, 3 unknown system. So that this node here, here, and here are the 3 nodes that I would write KCL equations at, with the bottom as ground. All right, let's do mesh just because that was the first thing that was suggested. So here's my mesh current IA. Here's my mesh current IB. So once again, we should see that IX is simply IA minus IB. We do have a current source in this case, so we have 1 amps is going to be equal to what mesh current? Negative IB. And so now we just have to write a relationship, a KVL relationship around mesh A. So that would look like 3 ohms IA minus 2 IX plus 6 ohms IA minus IB is equal to 0. So I'm going to just solve this system for IA, IB, and IX like I've done every other time. So in my first equation, my coefficient for IA is 1, my coefficient for IB is -1, my coefficient for IX is -1, my constant term is 0. So I don't need to make any changes whatsoever to that one. My second equation, I have a coefficient for IA is 0, coefficient for IB is -1, coefficient for IX is 0, constant term is +1. In my third equation, my coefficient for IA is 3 plus 6 is 9. My coefficient for IB is -6. My coefficient for IX is -2. And my constant term is 0. So when I solved this guy, I got IA to be -4/7 of an amp, IB to be -1 amp, and IX to be +3/7 of an amp. And now I could say that my test voltage, I'm just going to write some polarity terminals on here really quickly, is going to be the sum of the voltage drop across the 5 ohm resistor with this polarity, as well as the sum of the voltage drop across the 6 ohm resistor with this particular polarity. Okay. So that's going to give me V test is equal to 5 ohms times 1 amp plus 6 ohms times IA, which is -4/7 of an amp, minus IB, which will be +1 amp. So 5 plus 6 times A minus B. I got 53/7 of a volt. And from here, my Thevenin resistance is just V test over I test, which is 53/7 of a volt divided by 1 amp is 53/7 of an ohm. Once again, giving me the same answer that I got the previous two different ways we did it. Yes, ma'am. What do you mean for voltage? You mean V test? Okay. So I was using Kirchhoff's voltage law. So essentially I said this voltage rise is equal to this voltage drop plus this voltage drop. That's just KVL around that right-hand loop. The voltage drop across the 5 ohm resistors, I hope it's pretty obvious to just be 5 ohms times 1 amp. And then the voltage drop across the 6 ohm resistor is 6 ohms times IA minus IB. And since I have minus -1 amp, that's where that plus 1 amp came from in that expression. Any other questions about this guy? Okay, so just to recap, finding the Thevenin voltage for a circuit that contains a dependent source works exactly the same way as it did in a system that does not contain a dependent source. Finding the Norton current in a circuit that contains a dependent source works exactly the same way as it did in a circuit that doesn't contain a dependent source. It's only when we're dealing with Thevenin resistance where things can get a little bit odd, right? So to find the Thevenin resistance for a system that contains a dependent source, we can either find Thevenin voltage, find Norton current, and take the ratio of those two things, or we can convert our original system into a dead network and then apply a test source at its terminals. Doesn't matter if it's a test voltage source or if it's a test current source, and then find the ratio of the test voltage to the test current, which is just the voltage drop measured across the terminals and the current flowing into the terminals of the network, and use that to find RTH. So unless anybody has any further questions, you can start working on either your mini lab assignment or your in-class assignment.